Greetings and salutations, welcome to today's video on Level 2 NCEA Chemistry on structure and bonding. So today I'll just be going through the 2019 exam paper. Now how I tend to do this is that I'll just be recording one question per video because otherwise it will drag on for too long. Okay, so let's just get started. So this is by far the most attempted standard out of the three external standards that most schools offer. The reason being that this particular standard has really predictable questions, and you can rote learn pretty much everything, just grind through some past exams, and you tend to do quite well. So hopefully, but sometimes when you read the marking schedule, just bear in mind the marking schedule is written for teachers, it's not really written for students. You may find evidence that's a little bit ambiguous, or too simplistic. How much detail do you need to go through, or you simply just don't understand the concept, and that's where I come in to hopefully make sure you have a better understanding by the end of the video. So we'll be going through question 1, so let's get started. Okay, so question 1 of 2019's exam is looking at the solid section. So this is a very typical question, so hopefully you would have seen some of these table questions from the past exam papers. Now the reason why I put the periodic table there, you do get the periodic table in the exams, so it is really important that you know how to use these. Okay, so the most important thing that we will need to look at for solids is you need to be able to draw the staircase. Okay, now sometimes I draw it like that, staircasing down. It doesn't really matter because of the elements that sort of on the boundaries are not really metals, and they're not really non-metals, they're sort of in between. So it's like, say for example, silicon is kind of like an in-between element. It can behave really like a metal or non-metal, but why is this important? Because all the elements on the left hand side are metals, and then all of the elements on the other side are non-metals. Now hydrogen is an exception because it behaves like a metal, because it loses electrons when it bonds, but it's not a metal. Obviously, it's not a solid at room temperature. It is very volatile, so it doesn't count as a metal, but it behaves like a metal. That's why it's kind of in there, in no man's land on the top of the periodic table. Okay, so now, how do we look at this particular question? So bear that in mind. So let's look for sodium. Sodium is over here. Sodium is a metal just hanging out on its own, not bonding to anything else. So this is what we call a metallic solid, because you only have metal atoms. Okay, so you only have metal atoms, which is making this particular structure. Now the force of attraction between the particles, you are looking at metallic bonding. And what is a metallic bonding? Metallic bonding is the force of attraction between the positive nucleus and the negative delocalized electrons. But this particular question is only achieved, so we're not going to spend too much time here. Let's look at the next one, sodium iodide. So sodium is again circled there, and iodine is over here. So you have a metal and a non-metal iodine that are bonded together. So it is really important that you understand this is an ionic solid. This is an ionic solid because it's made of ions, positive ions, negative ions, and they are electrostatically charged to the oppositely charged ions, called ionic bonding. Now so you're typically looking for metal bonding with a non-metal. If you have a metal on its own, it's metallic. If you have a non-metal bonding with a metal, then it's ionic. If you have iodine, which is a non-metal, like we showcase here, it's a non-metal, just have an iodine bonding with an iodine, you form a molecule. So the base unit of this type of solid is called molecules, and this is a molecular solid, so this is molecules. So the force of attraction that hold it together are called weak. Well, they are weak, that's why I call them. I just chuck the word weak in there. Weak intermolecular forces. Now think of, like, say, especially if you play sports, let's say if you play inter-school sports, like say you watching this on the internet, so the word inter means between, so it's between the molecules, and that force of attraction is really weak, and that's really easy to break. Okay, now we're gonna go on to the next equation. So that's only achieved. Let's have a look at the next part. So sodium is malleable, where sodium iodide is brittle. So and one thing I tend to tell my students is that don't just be happy, if you can do one passing exam papers, you aim to do at least 3, because for this particular exam paper, the giant covalent network is not covered, and the melting point difference is not covered, the electrical conductivity is not covered, but then they are very, very popular questions that do come up quite frequently, just didn't come up last year. So what I'll do, I'll go through 3 years of exam papers during the school holidays that's coming up. So just you may want to come back and look at those questions if you still struggle with this particular unit. Okay, so sodium iodide is malleable. Sodium is malleable, whereas sodium iodide is brittle. Explain this observation by referring to the structure and bonding. So this is an excellent question. So you need to understand, first of all, sodium is a metallic, it's a metallic solid, like we described it just now. And what does it have? It has directional, it has, where's the rubber? It has non-directional bonding. It's non-directional metallic bonding. Now I'm just going to draw a diagram to showcase this, and then you can look at the model answers that I kind of typed up and combining with the NCEA marking schedule. Okay, so what it kind of looks like now, I can only draw it 2D. So this is a positive nucleus in a metallic solid, and what you tend to have, you just have layers and layers of these metal cations that are just in a 3-dimensional structure, and then you have delocalized electrons, or some texts will say a sea of delocalized electrons. So what it means by delocalizing is that they can just randomly move around, and then they can bond with any of these cations from any direction. Okay, so it's non-directional. So what it means when it's malleable means if you so the word malleable means if you, let's say, grab a hammer and then apply a force this way that is so strong, you might overcome some of these interaction between the positive nucleus and the negative electrons, but then the electrons can move around, or some other electrons can come into its place, and you will still maintain the solid structure. You will just make it into a different shape. You'll force the atoms to move around, but then the layers can, these layers of atoms can move around without actually disrupting its structure. So you can maintain a solid. I mean, the basic example you can look at, guys, is just going to your shower, have a look at the shower head, or just look at the water tap. Metals don't have those natural shapes. They are molded or hammered into those different shapes to suit our needs, because metallic solids have the ability to maintain the solid property when it's being hammered. Okay, because this is a key word here, it's non-directional. So if you hammer it or beat it, apply pressure, apply force, you don't break the structure. Now if we look at sodium iodide, which is a ionic solid, now this is made of directional ionic bonding. So this type of bonding is relatively strong, but what this kind of looks like, you have to have, so what it means by directional, it means you have to have the positive ions surrounded by negative ions, and negative ions vice versa surrounded by positive ions, because opposite charges attract and like charges repel. So if I have, you can clearly see all my positive, I can keep drawing this into a 3-dimensional structure. The positive ion is surrounded by negative ions. Now and vice versa. So if the same thing happens, if a force is applied from this particular angle, doesn't matter which angle. What it does is that if this was able to break that ionic bonding, you're forcing the positive ions to come into here, you're forcing these negative ions to come here, you're forcing the negative ions, so you're pushing all the ions further down. And what's going to happen is that this positive ion, when it comes to this position or this position, is going to be too close with this particular positive ion, and then this negative ion too close with this negative ion, and they will repel each other, and the whole thing just shatters. Okay, so that's why ionic solids are really brittle. Okay, so you need to be able to link the type of bonding, what the bonding actually does. Diagrams like these might help, but if you want to, again, this comes down to rote learning. This particular paragraph should really help you with this particular type of question. So you talk about what type of solid it is. You talk about, it's a 3D lattice held together by non-directional metallic bonding. It's non-directionally electrostatically attracted to the delocalized electrons. When a force is applied, they can move without breaking, therefore they can change shape. Whereas the NAI, the sodium iodide, is not malleable because it's directional bonding, and that forces the ions with the same charge to repel, to be next to each other, hence repelling. Okay, so this is an excellent question. It is to get, you can get a couple of achieves out of here really easily if you just, without even talking about, if you just mention metallic bonding is non-directional and ionic bonding is directional, then you got 2 achieved ticks, just like that. Okay, so another advice: never leave any question blank. It may look really long and intimidating, but if it's a calculation, if you just do one-step calculation, you might get an achieved tick. If you give some definitions or give some, correct facts, you might get an achieved bullet point, and that achieved may be the difference between an N7 to an A8 or a A13 to an M14. Okay, so you never know. Don't leave questions blank. Okay, so that's an excellent question. Let's move on. Now, this particular one is another excellent question. So this is looking at solubility. Now, a lot of my students tend to struggle with solubility. Here we are again. We're just going to go through this. So you can kind of think of this. So you have I2 in water. You have I2 dissolving in water. So think about this. Water, they told you it is a polar solvent. And then you got C6H12, which is cyclohexane, which is a non-polar solvent. Now, to help you with a bit of organic, just remember all the hydrocarbons are non-polar. Okay, so that might help in if we didn't tell you if this is polar, non-polar. All the hydrocarbons, like if anything, if it's alkanes, they're non-polar. Now we are putting iodine into this. Now iodine is a non-polar molecular solid, and you may go, how do you know this? So if you want to come back to this particular section, maybe watch question 2 of this particular exam paper, you may understand the polarity stuff a little bit better. So if you're able to identify this particular point, you get an achieved. Okay, so that's really, really simple. Now, to get merit and excellence, this is where a lot of people just fall short. A lot of people just write like dissolves like, non-polar, this is non-polar, this is non-polar, like dissolves like, therefore they dissolve, and you're not going to get anything out of that explanation, because that's not a scientific explanation. So what is a scientific explanation? So how does water, why doesn't I2 dissolve in water? So let's look at the water molecule, for example. So before we dissolve anything into the water molecule, let's look at the water molecule as they are. This is a polar molecule, so the hydrogen and a delta positive, they're slightly positive, and then the oxygens are slightly negative. Now this is a year 13 concept, but I don't need to tell you the year 13 stuff. You can just think about what polar means. It just means one side of the molecule is slightly positive and one side is slightly negative. Let's say if you have to watch this particular video from a screen, either your mobile or your laptop or your computer monitor, or even your TV. You can just look at your screen. You can think the top half of your screen, that's slightly positive, the bottom half is slightly negative. So if I put another computer screen next to that, you can see that the positive end of the of the water molecule is going to be attracted to the negative end of the neighboring molecule, because opposite charges attract, plus you got these negative electrons hanging here, making that even more negative. So what's going to happen is that they will have a stronger intermolecular force. So they don't physically bond, but they will have a strong intermolecular force between these water molecules. Okay, so this is what polarity means. Polarity means you don't have to have water as an example. You can have any polar molecules, and then they always have the reason why they're polar, because they have a positive end, negative end. If they have you have these guys hanging around with each other, then the positive end and negative end of the neighboring molecules will interact, and that is quite strong. Okay, so this is the water interaction. So this is the water molecule bonded with the water molecule. Okay, so why doesn't I2 dissolve in this? You put I2 in here, it comes in, you put I2, a bunch of I2s, lots of I2s into here, and the water molecules are charged in a way, and they look at the I2, it's like, you're neutral. You are not a very interesting molecule. We would rather hang out with each other, because this force of attraction is stronger than what an I2 would have with the water molecule. This particular force of attraction between the I2 and H12 is too weak, so it doesn't happen. So the water molecules prefer to hang out with each other, and the I2 has no other choice, and they just hang out with the I2. It's like kind of like going to a friend's party. You got people that really know each other quite well, and you're trying to blend in, and then you don't, because it's not your fault, because they just like each other really well. You just have to hang out with your own friends in that particular regard, and that becomes the rest of the night, that's your party. Okay, so that's why it doesn't dissolve. So but when you put I2 and C6H12, this particular force of attraction is okay. So before you put it in, you have I2 interacting with I2, you have C6H12 hanging out with C6H12. Now again, these are not, I shouldn't have drawn them like this, these are not chemical bonds. What you have here, these are I tend to draw them like these. These are intermolecular forces. So right now, the I2 intermolecular force and the C6H12 intermolecular force between the molecules is not that strong. That's why if you mingle these together into a big party, they're like, hey, I'm, nice knowing you, Iding, but I can hang out with the C6H12. He's not too bad, he's all right. And then C6H12 thinks likewise, you're not too bad, let's hang out. And therefore you have a dissolved mixture. So those two will mix together, and because this particular intermolecular force is stronger than the I2 and stronger than the C6H12, and that's why it dissolves. So if you talk about anything to do with solubility, so if anything that's soluble, that means the new arrangement is going to be stronger. The new arrangement is going to be stronger than what you had currently. Okay, so that's your general rule of thumb. And if you read the answers that we got here, this is what we're looking at. Okay, so same thing, but this is more acceptable as an exam answer. You just talk about I2 is nonpolar, that gives you achieved. It's made of I2 bonded by weak intermolecular forces. So it is soluble but not dissolve in the other. Why? Because in water, the iodine water attraction are not strong enough to overcome the existing iodine and the existing water attraction. So they just don't fit in, they don't mix. If you have iodine in cyclohexane, this particular attraction is strong enough to overcome the existing I2 and C2H cyclohexane C6H12 attractions, therefore it dissolves. Okay, so that's, to be honest, once you get the grip of this particular concept, it's one of those, I feel melting point and solubility are probably the easiest exam point, because once you get the hang of it, it's quite straightforward. Okay, let's move on to the next one. So this is the last part for this particular question. So this is actually an excellent opportunity, despite if you're reading the marking schedule, it is much shorter than the other two. But this is actually a quite important idea, because first of all, you have to understand you're going from solid to liquid. So this is your year 9 particle theory. Your solids are, they should be the same size. Your particles are really compact in solids, and then when you melt it away, you absorb energy, because if you don't absorb energy, they're not going to break, and they're not going to separate. Why do you need to absorb energy? Why do you need to absorb energy? Because you have to break the bonding, in this case intermolecular forces, but then we always go bonds breaking, bonds making for endothermic, exothermic, because, and I hate that name because you're technically not breaking bonds, but let's just go with the flow here. So because we need to break all of these bonds, like not all of them, sorry, if you broke all of them, then it turns into a gas, but you're breaking some of the bonds here, so you have to absorb energy, and this is confirmed by your positive change of enthalpy. Positive change of enthalpy means this reaction is an endothermic reaction. That means energy is being absorbed. Energy is absorbed. Now, so for this process to happen, they have to absorb the energy from somewhere. So if this is a beaker, this is my water, then right now it's not so cool. I'm like, that's not cold enough. Let's chuck some ice in there. And once you chuck the ice in, so the ice will start going. So this is H2O solid, and then what they want to do is that they want to melt and they want to dissolve, they want to turn into H2O liquid. So what that means, in order for this to happen, they must absorb energy. So how do they do that? Must absorb energy. So we're going to get that from, they're going to suck it in from all of the water molecules around them. So all the particles around these ice particles will start giving its energy to the ice to help it melt, and as a result, their temperature will cool down. So that's why the drink cools. Okay. So the answer that we kind of expect you to do is right here. So it is the melting of ice is endothermic, because you're breaking bonds, because you're going from solid to liquid. So if you're going from solid to liquid to gas, you are breaking bonds. And then and this is the beauty of enthalpy. If one side is breaking bonds, if you go this way, that means if you go the other way, you are making bonds, because one way you can think of it is that you are forcing particles to stay together, and they're more stable that way, therefore they release energy. So that's exothermic. Okay, so breaking bond is endo and making bond is exo. Okay, and that results cause the temperature to decrease. Okay, so hopefully that was helpful enough. Now if you did find this particular video helpful, please because this is my first video, if you could subscribe, comment if you have any other questions, and share this with people in your class or in your school. That will be greatly appreciated, and hopefully we can collectively improve our results in chemistry and gain better understanding of this particular subject. Otherwise, take care, and we'll see you next time.